whole online thing in total. Okay, so let's go to Files, and let's talk about the funness that is gravitation. So we already saw the introduction to gravitation last week on Friday, and we talked about Newton's universal law of gravitation. All right, and we talked about the force of gravity here being between any two objects in the universe. All right, M1 and M2, and that's constant. And we introduced the first of basically three fundamental constants of nature, right? If you remember last week, I told you that, I'll pick another color, that G is our physics 1 constant, C, the speed of light, is our physics 2 constant, and H, or H bar, you can do either one. Basically, in case you're curious, H bar is just equal to H over 2 pi. So it's just a scaling factor. But that's your physics 3, your modern physics constant, okay? So, so basically, we don't have to worry about these yet, right? We'll just concentrate on G. But you can see where it comes here in this universal law of gravitation, and you can see that G is small, right? This means that the forces between any two masses are very, very low and can't overcome friction typically. This is why when we look at this type of gravity, universal gravitation, it generally makes the most sense between objects that aren't in contact with anything, like the moon and the earth, or the sun and the earth, or planets revolving around stars, right? There's no contact friction there. However, you do not attract your siblings, or the largest person in your house is not a gravity well, because the forces that you get are very small. And in fact, I think they say something about that here, don't they? We went over those checkpoints last week. Nope, that's where I wanted to start today. I thought I remember them saying something about, yeah. So for two people, the force between them is less than 1 micronewton. All right, and 1 micronewton ain't overcoming friction. Usually I'd say we've seen that in the lab, but I know we didn't do that lab, but we did do something similar, where hopefully you saw that the frictional forces are on the orders of 1 newton, or 10 newtons. So that's 1 million to 10 million times stronger than this number here. Okay. Now, we talked about systems of particles, and I want to talk about that again, because when we talk about universal gravitation, it can become very counterintuitive, because a lot of the things we talk about have to do with the system, right? It doesn't make sense we can analyze any of these two objects, but the system doesn't make sense if we delete one, right? Because the force is due that product of the two masses, and I'll write it again. Universal gravitation. Over r squared, okay? So you can see here that you need these two masses, right? You have to have a system. It doesn't make sense individually. And we talked about the shell theorem, which I'll let you review on your own. But the important part here is that what you get is a pair of forces, right? You'll notice all the analysis is done on particle 1 here, right? So you'll notice all the forces, radial, the vector, all the vectors, the force vectors are indicated on particle 1, and the radial vectors here too. But you could change your perspective to the second one, right? And actually, what you'd want to do, I was about to make Professor Tolan's first fun mistake of today, but I'm going to correct myself. You probably want to keep your r vector along the same r axis, just because now you can see when you do it that way, when this is r hat, or when this still is r hat, you can differentiate between these being positive and negative forces. And I'm pointing to these two right here, right? And you can see they pull towards each other, but by keeping R consistent, these have will give you the correct directions relative to each other. Okay? So whichever way you do it. Now, that being said, you can pick R either going this way or back down the other way, and you'll get the same, you'll basically get essentially the same answer. So it doesn't matter which one you pick, but once you pick it, you have to be consistent. And I don't know, I reflect on that point. That's I think one of the more counterintuitive parts of all of physics. If you really look back at the course, you have a lot of freedom of things you can pick. Where things become problematic is once you pick something, you no longer have that freedom, right? Once you say the origin is at a spot, your origin's at that spot. Everything has to be done with respect to it. Once you pick your rotational axis, that's your rotational axis. Now you need to analyze the problem. So sometimes it can be confusing because you'll think, oh, I still can just pick whatever I want. No, you can't. You have to be clear and go through it. You know, consistent. Maintaining consistency is important. Okay. So we saw that in our everyday lives, and I want to point out something to you that I'm not sure when they get to it, but I just want to get to it now. But I want to look at a system in terms of chapter 2, and then in terms of chapter 13. All right, so the chapter 13 system is the one with the Earth and the apple. Chapter 2 is just the apple. So with chapter 2, we would say that let me get the right colors. We would say that the force, that 8 newtons, you can get by multiplying the mass of the apple times g, right? That's what we would come up with. And you'll notice they get F equals 8 newtons. That's the force of the apple falling down onto the ground. Now, so that's chapter 2. Now, in order to understand this, you might be saying, well, wait a minute. We just saw that F equals G m1 m2 over r squared. But remember that F always equals ma. That's our big equation, right? So when we do that here, we see that our acceleration is equal to g, right? When we do this here, I'm going to do m1a, and I'm going to choose m1 because we're looking at the apple in virtually all of these situations, right? So m1 is the apple, m2 is the Earth. And what we can see here is that a equals g equals big G, universal gravitational constant, times the mass of the Earth, I'm going to put planet, over the radius of the planet squared. And we can use the radius of the planet, right, because the diameter of the apple plus the radius of the planet is about equal to the radius of the planet, right? The apple doesn't change your elevation in any appreciable sense that we can measure. Okay? So we're going to see that with this kind of system, we're able to actually solve for that even though the forces are the same, right? So there's not only a force of the apple on the Earth, but a force of the Earth, on the apple from the Earth, but there's a force on the Earth from the apple that is also equal to 0.8 newtons. But you'll notice that the acceleration of the apple is equal to g, and this is this tiny acceleration, which we pointed out would take forever to accelerate to. Okay? And so the point here of the review is to look at things in terms of the system, right? You have a system of particles. This is going to become critically important when we talk about energy as well. But before we get to energy, we have to flush out more of our properties on forces. We did that checkpoint last week. And so now we want to talk about gravitation and the principle of superposition. So the principle of superposition is going to seem fairly straightforward, but it's very critical because it allows us to add many things up. All right? And basically the idea is that all you have to do is that basically the principle of superposition is that the sum, the whole, or that the whole is equal to the sum of its parts. All right, so you'll notice find the net gravitational force by principle of superposition. You can find the net gravitational force, that's the whole, by adding the sum of the individual effects, sum of the parts. All right, and you can see it here literally. Here's the sum, right? Here's the individual. So what this would look like expanded in a more in a more classic way is you would say that F1 net, that's all the forces on particle 1, equals F12 plus F13 plus F14 plus ... Okay? And if you want to picture something, let's we can say, we can make a little coordinate system, and we can put F1 here at the origin, 1, and then if we make little dots, right, maybe 2, 3, 4, 5, and 6, you can sort of see how this goes. So basically, to find the net force, you can just break this up into 5 little problems, right? You're going to be attracted to this mass, you're going to be attracted to that mass, you're going to be attracted to that one, you're going to be attracted to that one, you're going to be attracted to this one, right? If they're all in a vacuum, you can simply use Newton's law of gravitation and for 2 masses, right? And again, we'll write it in a corner over here so we can get the context. F equals G M1 M2 over R squared, right? So you'll have 5 terms in the sum. If you add them all together, you get the net force. All right? It's one of those subtle things that it's pretty amazing that it seems almost trivially obvious, but it's pretty amazing that it works and is consistent. All right? Because again, we can break things into components, and these properties still hold. Now, of course, whenever we have a sum, we can take the limit of that sum to be continuous, right? The sum is discrete, and if we take it to be continuous, we get an integral of df. All right, so if the object is a uniform sphere or shell, we can treat its mass as being at its center of mass instead. But not everything is uniform, and that will have consequences. All right, so if we look at this example of summing 2 forces, so we want the forces on particle 1, not the forces on the other particles. All right, so basically we're looking at an example of how to find, the question is basically what's the net force from the particle systems, or all the particles in this system on M1. Okay, so we break it into 2 separate little problems. All right, so we can do that. You'll notice they do that here. We can see that M1 is attracted to M2 because gravitationally everything is attracted to everything else. And so we have that force vector, and then M1 is also attracted to M3. Okay, but you'll notice, so to get the magnitude is trivial, right? We just have F1 net. Well, first let me ask you a question. I'll do it over here actually, because it's, how many terms are going to be in this equation? So we have to sum some stuff, right? How many terms will there be in there? It should be pretty obvious looking up there. 2, very good. So we have F12 plus F13, and that's going to be equal to G M1 times, let's see, M2 over A squared plus M3 over 4A squared. All right, so that's just using Newton's law and doing the math and sort of rearranging everything into something easy. So I'm hoping that that magnitude is just straightforward. You plug it in. It's the net direction that can be difficult, right? So you start, but again, you start with it the same way. You just have the direction from one mass, and that'll give you F1 and the force from the other. Now, we're assuming here that these masses are the same. So if that's true, right? If M2 and M3 are the same, it'll be pretty obvious that since the denominator is smaller, this contribution will be bigger. But that may not always be the case, right? So basically, from your magnitudes, you'll have to confirm whether the size of the arrows are correct. And from there, let's just say you did that, and this happens to be the case. That way, we're not making stuff up. So making stuff up is always a bad idea, right? We always get into trouble when we make stuff up. Yeah, Fatima.
I just don't understand how you got A squared for the first term and then 4A for the second term.
Good. Good question. So let's recall that F between any two masses in the universe, right? F is equal to big G M1 times M2 over R squared. So this is an inverse squared law. So the distance between M2 is A, right? So for R squared there, that will equal A squared. That's what I have to plug in, right? Is this A has to be squared. And then for down here, R is equal to 2A. Therefore, or for M3, R is equal to A.
I'm sorry. I just didn't pay attention that they called the distance A. I thought it's acceleration. I was like, what does have to do with acceleration? I forgot.
Problem.
Sorry.
It's overloaded, and
this too
if
small,
they were smart, they would pick D or F or something. Yeah. No, that's no problem. I think it's a good question. It highlights the square dependence of the or the inverse square dependence on the distance. So when we look there, now that we have these two vectors, all we have to do is I'm hoping now at the end of the semester, the reason you have an extra credit, if I was going to give you an extra credit homework assignment, it would be to do a bunch of vector problems. You'll see we're still using vectors in vector addition to get important information in chapter 13. So what you can see here is that you can add these vectors, right? You can just parallel transport this one up here, and then you get you can just have the use your method of connecting one arrow to the other, and you get the direction of F net. Okay, and this is just showing you can do parallel transport the other vector if you want, and you get the same thing. You'll notice with the given material, you have to be careful which way your angle's pointing. If you get something like -76, you'll notice that it's not the correct quadrant. That's a quadrant 4 angle, where you clearly have your geometry shows you should be in quadrant 2. So you need to you'll often need to double check that with these problems. All right, you have to make those distinctions a lot more. It doesn't just sort of automatically fall out. Again, that has to do with the fact that you're picking the origin, you're picking the orientation, and so once you do that, you have to remain consistent. Okay? Any further questions on this part of it? All right. So let's do a checkpoint then to make sure there's really no questions. So the figure shows 4 arrangements of 3 particles of equal masses, right? Okay. So we want to rank the arrangements according to the magnitude of the net gravitational force on the particle labeled M, greatest first. So let's do that, and then we'll worry about question B. All right. So again, you notice you have all of these. You have your particle labeled M. So which one of these will be the greatest, and which one of these will be the least? And again, I want to remind you all that your universal gravitation okay? So that should help you out. So remember, don't just think of the magnitude, you got to think of the direction too. And remember, gravity is always attractive. So keep that in mind. Four is at a right angle. Yeah, it's a right angle, right? I see. They explicitly said it here, but they did not say it. Yeah, you can take 4 to be at a right angle. All right. If you look at it, take a look at how everything's adding. Think about the net vectors. So if you have M in each spot, right? If you're struggling, draw the vectors. So you have one here, and you have another one over it. These two add, right, to make one long vector. So see if that helps, if you don't get it. So I would say, Nicholas, almost, right? 1 is definitely the biggest, and 4 is definitely the small, or 3 is definitely the smallest. But is 2 bigger than 4? 2 and 4 are the same, right? So you want to put 2 and 4. And we can see that by adding the vectors. You'll notice here M is attracted to both. So while before it would add in 1, in 3, those are opposing, they'll subtract. And then you'll notice that you basically have the same components here. They may be flipped, but the direction will essentially be the same. All right, the orientation between them is the same. So that will make 2 and 4 be equal. All right, because you'll have one, M will want to go this way. You'll have a triangle there, and you'll have the same triangle just rotated. Right? That doesn't really change much. Okay? So that's that. So let's do B now. So in arrangement 2, is the direction of the net force closer to the line of length D or that of line big D or little d? Yeah, I would say it's going to be closer to this D because this is going to be the bigger arrow, right? Because both masses are the same. You move them farther away. That's how that works, right? All right. So as we can see, yeah, we have our nice solutions there. And it's a little premature, but I want to just take a break. We're about 5 minutes early on the break, but that's okay. We'll get to the gravitation near Earth's surface when we come back. So let's come back. Let's not take too long though. Let's come back around 8 or 9 after. We'll try to get started by 2:10. Okay, and get through the rest of chapter 13. All right, I'm back. Got some water. How many more chapters do we have? We have basically this one and the next one. So that's chapter 13 and 15. And then we are pretty much done. If we have time, we'll go over chapter 14, but I don't want to give up on that. All right. I don't want to give up on chapter 15 because that's the stuff you really need for physics 2. Okay. So this is a short exercise we'll do. We already saw this result, right? That we can combine Newton's second law with our universal gravitational law, and we can derive the acceleration for gravity on a planet or the acceleration due to gravity based on how far we are from the distance of the planet. And you can actually see here from this table that the acceleration of gravity will change based on where you are. But you'll notice that even at the highest point in Mount Everest, right, you only go from 9.83 to about 9.8. And at the highest crewed balloon, you only lose a little bit more. That's an altitude of about 36.6 kilometers. So you'll notice at a space shuttle orbit of about 400 kilometers, you're only down to 8.7, but by the time you get down to a communication satellite or GPS satellite, this acceleration is pretty low. Okay? So we already derived that, so there's no need to spend a ton of time on it. But of course, the calculated AG will differ slightly from measured G at any location. All right? Therefore, the calculated gravitational force on an object will not match its weight for the same 3 reasons. So the Earth's mass is not uniformly distributed. You can see here, the density changes of the Earth will change. The Earth is not a perfect sphere. It's not to say the, oh, Jesus. Having it being hard to talk with the tooth is not a good thing. I just need one, Jesus. I just need, need a second here. I got to figure this out because I have a whole other class after this. So the Earth is not a perfect sphere. So the Earth is spherical-like, but it actually bulges a little in the center. So my imperfect drawing is a little more accurate here. So I'm not trying to say we live in some sort of flat Earth. There's no conspiracy here. It's probably better to say that the Earth is not a perfect sphere. It's a spheroid, it's spherical-like, but it's not a perfect sphere. And finally, the Earth rotates. So these will all throw off your calculated G, your experimental, or your theoretical, sorry, with your calculated G at any location. Egg shape might be a little much. That might be a little too extreme. It would look more like a sphere than an egg when you look at it from far away, but its variations are enough to be important. They're not enough to see with your eyes, maybe, but you'd be able to see them like that. Yeah, you wouldn't confuse the Earth with a potato or an egg. I think you would see you would think of it and say, oh, it looks like a little blue marble. So we can actually see the difference in gravitational force and weight due to rotation at the equator, and we do this, right, by looking at this part of it. You have a crate with the normal force, right? So you have, that's the normal force, right? Then you have the weight. So that's what's going on these two sides. And then you have mv squared over r, which turns into m omega squared times r. All right. And if you're looking on this particular, let me see, you have this. Right, so we're rotating. So if we're on the crate, if we're on top here, then we have to be in that minus direction because that's down, right? Positive would be out this way, and that's just not true. So our acceleration is towards the center of the circle at that point if we're rotating. So we have to keep our signs there and consistent. And you'll notice that G equals AG. Right. So Fn, this normal force, you'll be able to reduce it and get add this to the other side, and you get G equals AG minus omega squared R, and you can see how the rotation of the Earth will affect that value. So what would be interesting in a follow-up lab perhaps is to see if you can figure out discrepancies in what would have been your free fall experiment, right? With the rotation of the Earth based on your location on it. Keep in mind that this is at the equator, so the term here in New York will be, will be a bit different. I believe this whole thing is a maximum at the equator, so we'd have a smaller value. Okay. So now we want to go to gravitation inside the Earth. All right. This is an important thing to look at because this is a skill that will be important in when it comes to physics too. So clearly, we'd see what happens outside, right? If we're outside, if our point of interest is outside the Earth, we can treat the Earth as a point, and we can then apply the universal law of gravitation. But you'll notice something interesting here, all right? So if this law is true, m1, m2 over r squared, right? If you look at this, what's the limit as r goes to 0? As you shrink the distance, basically, as you go inside the Earth and make these two masses smaller and smaller, what would you expect the force to do? Get bigger or smaller as you bring them together? You'd expect it to get smaller, so that's good, and that's what will happen, right? Your intuition tells you that at the center, the force should be 0, right? If you're inside a mass, if all the mass is outside of you. And that's true from symmetry. You can even see that symmetrically. But what does the math say? Take the limit as this goes to 0, as r goes to 0 of f. What's the limit as r goes to 0 of f? It increases by a lot, right? It's infinity. So if we look at it from the equation, it looks like it should diverge, but our measurements and our intuition tell us, well, wait a minute, if we're in here, all the mass, a mass from here is going to be the same as one from here, it's going to be the same as one from here, the same as one from here. They should all cancel out, and your force should be 0. So you can see symmetrically that f should be 0, and 0 is very much not infinite, right? Not even in some cool I'm on drugs sort of way. So what we have to do is we'll look at this, and you'll notice we have our we'll start with universal gravitation, but we have to look at the mass inside the planet and how it changes. All right? And that will be the important part of the next thing we're going to do. All right? So basically, one of the I've pointed out to you a couple times in this class, it'll be, again, more important in physics too. One of the powers of density, right, is we always say, oh, well, it's just mass over volume. but it's also equal to, we saw this with the rotation stuff, dm over dv. All right, so now, assuming a constant density, we can say that the density of any differential part of the Earth, right, this is any fraction you take, is equal to the density of the whole thing. The density is not going to change. Okay? So in this sense, we can solve for the mass inside, and we get m inside equals the 4/3 pi's will cancel, will be equal to m r cubed over the radius of this, the radius of the planet cubed. Okay? So that's just the fractional volume you can see that you have. And now plugging mass inside into gm, so F equals G, m inside m over r squared. This is going to now equal G, we'll do little m, and we'll call this big M r cubed over this fixed radius cubed times r squared. You'll notice these cancel, and you have this new equation. All right, and why is this important? Because you'll notice that at 0, F equals 0. Or at r equals 0, F equals 0, which your symmetry and your physical intuition will tell you. Now, if we write this as a vector equation, substituting for the constants, you'll notice we get what looks like Hooke's law. So what does that mean for our example? So let's go back and look at the original problem in the example. So the original thought question here, after sort of learning all that, is what happens if you dig a hole on one that goes straight through the Earth and jump, well, I forgot that I'm not in class. You jump straight through the Earth and you go down. What do you expect to happen when you get to the other side? Ignoring heat and lava and all that good stuff. A thermally insulated tube, what would you expect to happen? Well, you can see from the example that if you jump in, you will start to fall like anything else, and it's only if you hit a surface or something here that you have to worry about splatting. But much like a spring, you notice you'll start to increase, your velocity will increase, but now as you come over here, right, most of the mass, you're always pointing towards the center of mass. So now here, your acceleration will be pointing opposite your motion. So you'll actually start to slow down. And when you get to the other end, you will have a nice, slow, zero velocity, which you can, you know, if you have a bar or something, you can extend it and then stay on this side of the Earth. And this would actually take you from one side of the Earth to the other in a really fast amount of time. So it's the only way to travel, if one could travel this way. So, looking at that, we can see that we have this Hooke's law type of behavior, which means that you'd actually go back and forth like a spring if you went through the center of the Earth. Now, I want to get to, we're going to cover this whole chapter, but this is the last part that will be on the exam. So, for chapter 13, only 13 through 13.5 will be on the exam. I'm going to talk to you about Kepler's laws in astronomy today to sort of take us, finish out the day. But we're not going to do examples and things with it. I mean, we'll do light stuff, but I just want to give you the context because that's interesting context. But I do want to save time. Be sure that we do get to chapter 15 tomorrow and the next day. So gravitational potential energy. So we have to go through a few bullet points here. And again, these bullet points highlight each individual part of the particle system. And when you look at gravitational potential energy, it's going to be even harder, if not impossible, to associate energy with any one part, but to look at the system of a whole. So you can look at the energy of a particle as it interacts or moves away or towards the system, but that requires you to know the whole system. So let's look at our notes and things we have to look at for gravitational potential energy. So the first bullet point here will tell us that the gravitational potential energy is a property of a pair of particles. I just said that, okay. But I think I would amend this to a system of particles, all right? You can have components, so each term will consist at least of a pair of particles, but really it's the system that you have to look at, okay? So we cannot divide it up to say how much of it belongs to each particle in a pair. We also sort of said that, but it's good to be explicit, right? We often ask of the, we often speak as of the gravitational potential energy of a baseball in a ball-earth system, all right? So sometimes we're just being a little sloppy. We get away with this because the energy change appears almost entirely as kinetic energy of the ball. But this is only true for systems where one object is much less massive than the other. So basically, because the Earth is so much bigger than the objects we deal with every day, it lets us deal with a simplified system where it can seem like we only consider the object, but it's sort of implicit that the Earth is involved. All right. Okay. So when we do this, we can write the gravitational potential energy with this expression. It's equal to minus GMM over R. So the minus sign and the R are sort of different from the forces. You're actually going to find that you can derive this from our definition of work, okay? And we'll take a look at that in a minute. But we want to note that the value is negative and approaches 0 for R equals infinity. So basically, at infinity, there's no energy exchange between the particles, right? At an infinite distance away, they can't interact with each other, therefore there's no energy, all right? And again, much like with forces, the gravitational potential energy of a system is the sum of all potential energies for particles. So you'll notice that you have your system of particles, you have to sum the interactions. So let's look here, and you'll notice that I'll do it in 3 colors, that there, for 3 particles, you have, I was supposed to do this in different colors. Sorry about that. You have 3 pairs, which I'm circling here, and a red. All right, and everything we need to know is here. And so you'll notice that we have 3 pairs, we have 3 terms in the equation, and you'll notice here you have to look at every possible combination to get the potential of the system. You'll notice they factored the minus sign out, and again, it's over R, not R squared, but if you remember, work is equal to the integral of f dot dx, right? So we kind of know that we're going to integrate 1 over R squared to get that this potential, right? Because you can use our work energy theorem and things like that, and that'll help us, you know, figure out the signs. But we know we're going to integrate that force term. When we integrate it, that R squared will become an R. Now there'll also be negatives going on there as well. So keeping track of signs with energy is going to be extremely important. Okay, so you'll notice we start here to derive this equation with our vector integral, except we put some limits on it. So we always go from the position we're at out to infinity. And again, remember that the energy at infinity is 0. All right? So the integral contains that dot product. And again, this has always been here. And so we can replace the vector dot product with this sign here. Now again, we've always done this, but this term has always gone to 1. All right? Usually these are in the same direction or something like that. If they were perpendicular, then that term could be 0. if you look here and you put in 180 instead of 0, you get a negative sign. And so F dot dr, and you put in Newton's universal law of gravitation for F, becomes this term here. All right? Now again, let's take a look at that picture-wise. All right? So we have, let's just look at two objects. So this one will be fixed. We'll call this M. So M is attracted. Again, we have to be consistent along our r hat vector. However, we're moving from r, which is this distance, to infinity, which has us moving in the negative r hat direction. That's where this 180 degrees comes from. It's not just being made up. And so here we can see that we remain consistent. And again, we have this and this. Now, when I'm integrating and doing calculus, I am not a fan of the quotient rule. And so essentially how I would write this is I would write this as minus g m m r to the negative 2 dr. That makes things a little clearer. And yeah, and that can just be integrated up very simply. So when we do that, you'll notice this factors out, and you have, again, I would just do it as r to the negative 2, and let me show you why. I think there's always a weird minus sign missing here. So if we integrate r to the minus 2 dr, we should be able to add 1 over 1. Ah, right. So add 1 over that same 1. That's going to be equal to r to the minus 2 plus 1 over 1. That's going to equal r to the minus 1. Right? I feel like I'm missing a minus sign here. Because if I take the derivative of r to the minus 1, that's going to be minus 1 I always get stuck with something here. Because if you look here, they just flat up say it, that the derivative of 1 over r is 1 over r squared ddr. But that's not right. Because if you take it down, it's x to the minus 1 will be, that derivative will be minus x to the minus 2, right? That's how that's supposed to work. So there is a minus sign somewhere here. Ah, I see what they did. They did do the minus sign, but then they just canceled it out here. All right, see what I mean about keeping track of signs? You've always got to keep track of the signs. So good, so everything's fine. We have this, this minus here. And that works because then we get this whole thing simplifies to this evaluation. And you have the minus times the minus that comes from the integral will equal the squared term here. All right? And now we can just plug in everything. So we can write g infinity down here, which will be 0 effectively. The mathematicians won't like it, but that's okay. Minus gmm over r, and that equals minus gmm over r. And that is our work function. So we now have the work, right? Work is required to move the ball from point P to infinity, or from R to infinity, okay? And delta U equals minus W, our work energy theorem, tells us that we can also write the work in terms of potential energies, as U at infinity equals minus U equals minus W. And so we have this is 0, right? because we've already defined that. So the work energy theorem here isn't just U equals minus W, it's the change in U. So this implies that minus U equals minus W, or W equals U, all right? Or is equal to minus GM M over R. So that's how we derive that, getting all the signs right and keeping everything well there. Just watch out for your floating minus signs. You'll notice we change them a lot. So you want to be very, very careful with your bookkeeping, okay? And this is going to be incredibly important for looking the study of electric and magnetic fields, which will be a large part of your Physics 2 course, because you'll use the same techniques in studying both of those objects. Okay? So the gravitational force is conservative, which means the work is path independent, so it doesn't matter which way how you get there. And since the work is independent of path, the gravitational potential energy change, the work energy theorem, holds, which we just saw, and that will lead us to our our derivation. But we can also see here that Newton's law of gravitation can be derived from the potential energy formula by taking the derivative, right? So we can take that derivative to get the force. Now they want to talk about it this way because when you do more advanced physics, you start with the energy and get to the force. All right, so identifying that's what's sort of weird about this class is overall we start with F equals ma and we derive a bunch of stuff and we can see that it's sort of circular. But the reason they want to present it this way is because as you get more advanced, you can't start with forces and always get an energy, but you can almost always start with an energy and get a what we call an equation of motion. Okay, so one of the first applications that we can look at this is a projectile. For a projectile to escape the gravitational pull of a body, it must come to rest only at infinity. So if at all, all right? So at rest, or at infinity, that means that the total energy, right, K plus U, is going to equal 0. Because if you're at rest, K is equal to 0, and we've already defined that infinity, there's no potential between the objects. Now, let me just make sure. So if K is the kinetic energy at the surface of the body, all right, and U is the gravitational potential from infinity to the surface of that body, you can write that the total energy, K plus U, is going to be equal to 1/2 mv squared plus negative gm m over r, but that total must be equal to 0. And then from there, you can solve this pretty directly. The m's will cancel, the little m's, and you can get the escape velocity from an object. Now, I want you to be aware that the escape velocity is not the orbital velocity, all right? So if you look online, you'll notice that the rocket to the moon is huge, while the space shuttle, while big, is much smaller. And the space shuttle never escaped the gravity of the Earth. It was meant to service things in low Earth orbit, which, as you saw, the Earth still played a large part. But in order to completely escape the velocity of the Earth, you must have you must get to a velocity of 11.2 kilometers per second. All right, not per hour, per second. All right, so you have to go pretty darn fast relative to the Earth. And you'll notice, of course, that the larger the mass, the larger the escape velocity. So in order to escape the sun's gravitational pull, those small Voyager satellites had to have this type of escape velocity. All right? And that's why we often call them the fastest man-made objects ever made. And of course, for larger astronomical objects, you have to get way, these become very big. And if you get to a black hole, the escape speed is greater than the speed of light, which means that no light can escape a black hole, hence their name, black. Because no light can escape, no color can escape. Fun fact, with frequencies, color is defined by a set frequency. So black is often a perfect absorber and white a perfect emitter, and they usually contain all frequencies, so they are in fact not a priori colors because they don't have a single frequency. So I don't want to do that one. I'd rather do let's see what time is it. It's 2:42. So let's take a look here at this problem. An asteroid is headed directly toward Earth and has a speed of 12 kilometers per second. Everything you've ever seen is every color but the one you see. Well, yeah. Well, the color you see is the one that interacts with your eye, right? So I mean, before getting too crazy, we can measure frequencies very accurately. So sensors that detect color are what you have, but certainly everything absorbs a lot, right? So I'm looking at a blue wall. That's absorbing all sorts of colors, but it's reflecting, it's transmitting only one color. It's not transmitting all colors. All right, so. But I think I kind of see where you're going there. All right, so let's take a look here. An asteroid headed directly toward Earth has a speed of 12 kilometers per second relative to the planet. When the asteroid is 10 Earth radii from Earth's center, that's how much it has. Neglecting the effects of the Earth's atmosphere on the asteroid, which will be large, find the asteroid's speed when it reaches the Earth's surface. So in order to solve this problem, I want you to note that it still requires the same skills from our energy unit. And I'm kind of glad you're working on the energy labs because for some reason recognizing this part, although you guys did well on this second exam, so maybe it's not as hard as it seems, equals K plus U, right? Initial and final. All right, so we want to draw it. We have an asteroid, and we have the Earth. So that's 1r. And this distance here is 9r. You want to be careful, right? It gave us that the distance to the center was 10 r, where I'm just writing here as r equals Earth radius. Okay, and we want to know what the velocity is when it reaches the surface. So we know that Ki equals 1/2 mv squared. And that's going to be minus g m Earth over r initial, right? And then that's going to equal 1/2 mv final squared minus gm me over r final. So we know things we know. Do we know the mass of the asteroid? No, but we don't care because it's in every term. It's going to cancel. So let's use a different color to do some analysis here. We know our initial and our final, right? Our initial is equal to, so from the Earth's surface is equal to 10 Earth radii. And our final is equal just to the radius of the Earth. Okay, so we have known values for RF. You can look up the mass of the Earth on a table. That is information. You might ask, how do we know the mass of the Earth? That's a good question. We're actually going to answer that in our discussion portion of this stuff. But G is a constant, so we know that. 1/2 is there. V2, or V initial, right? There should be an initial, not a 2. Is equal to 12 kilometers per second. So we know this. So rewriting everything, we have 1/2 V initial squared minus G m of the Earth over 10r the Earth, and then we're going to move that to the other side, plus GME over radius of the Earth, right? And that's going to equal 1/2 V final squared, and we can rewrite this as V final will equal, we're going to make a parenthesis here, V naught, V initial, minus, or hold on, plus GM mass of the Earth over the radius of the Earth, right? Which is actually equal to little g. So no, over r squared would be little g, but you can sort of figure that out easily. But then you can write this as, factor that out, and then have this as minus 2 over 10 plus 2. Okay? And then that will all be to the 1/2 power. Right? That'll be square rooted. And so as you can see, it's actually pretty, uh-oh. That's not good. That is not good at all. All right. It's just during the summer months, my power has issues. So it seems to have worked itself out. So that's how you set that up, and that should be pretty easy. Things to look at: you start with conservation of energy, and you just keep going. All right, and that should give you your final value. So, questions, thoughts? Okay. So what I want to do now, I understood why my Tuesday classes had low attendance because of the irregular day, but I'm sort of worried that we only have 14 today. I don't remember saying class was over, but I'm going to take the attendance, and I got to do that at some point. So what we want to do is we will move on to our discussion part. All right, so we're going to talk about astronomy for a little bit, and we're going to answer that most important question: how do they get the Earth's mass anyway? It's actually not hard to measure the mass of the Earth. Now, in order to understand this stuff, though, so again, you can kind of relax here. We're just going to talk for the next 25 minutes or so about astronomy and Kepler's laws. So in order to understand the context of which this is being asked, you kind of have to understand, well, in order to understand why this is important, we have to understand the context of how Newton's laws in physics were developed in the first place. So the first thing that, Newton's laws were developed really to describe bodies in motion, that's the stars. And I think I talked about this last time, where the Earth being at the center of the solar system versus the sun being at the solar system is actually an argument, a scientific argument, that before the data the telescope provided was available, each had pluses and minuses for being a legitimate for being the correct scientific theory. They're both legitimate scientific theories. One is just incorrect. It doesn't have evidence that supports it anymore, but it used to. So, so again, what was puzzling is, and I'll mention it again, is imagine you looked at the night sky, and imagine you're doing any experiment, right? Now imagine you had 2,000 data points, 2,005 data points. 2,000 of those data points move exactly perfectly with your theory. All right, that theory being the Earth is at the center of the solar system, or the universe rather. But you have 5 points that just don't add up. All right. Now, if you had data and you had 5 points, most of you would probably throw away the 5 points. And that's exactly what people did for essentially, 2,000 years. And what the points they were seeing are these planets is what we call retrograde motion. So you'll notice that you have June, the planet starts to move backwards in this weird epicycle motion, and then goes forward. Now, this could easily be explained by putting the sun at the center, and you might say, well, then why did they do that? Well, there's a huge problem with the sun being at the center, which is that no one observes stellar parallax. What is stellar parallax? Put your hand between your right up to your nose and blink your eyes. If you call one of them January and one of them June, all right, every 6 months you would expect the stars to have that parallax. It's not visible with the naked eye. And it was impossible for the ancient people, or not even ancient people, but it's hard for people to comprehend that they can see something that would be so that the sizes of stars and the distances they are away were just incomprehensible because you could see them, right? So the thought is, if you can see it, it must be close enough to have parallax. Everything you can see has this parallax. You can see stars, therefore they should have parallax. You can understand the argument. It wasn't seen. This was a huge problem in the development of moving away from the Earth being at the center of the universe. It really was data driven. It wasn't. It became part of religious doctrine of the day, but that's just because it was religious doctrine trying to absorb the science as part of its explanation, not the other way around. But it was that way for so long that it was a huge shift in the way people thought when Galileo applied the telescope to astronomy, and that led to some inconsistencies. Right? It showed that one, not everything orbited around the Earth, because you could prove, and I think someone said in here yesterday, you could see moons, you could see phases of Venus, which prove that Venus rotates around the sun, not the Earth. You could use the telescope to prove that Jupiter has moons that rotate around it, not the Earth. And then you could also resolve the Milky Way as individual stars. Now, from that point, what happened was people decided that, well, we just need to take more and better data. And a gentleman named Tycho Brahe took very accurate data and took the most accurate stellar data up to that point in the late 1500s. And basically what he did is he gave it to Kepler to analyze. All right? And now Kepler came up with 3 observations, which he called Kepler's laws. All right? So Kepler, by looking at the data, said that all planets move in elliptical orbits with the sun at a focus. We can see that here, right? Not a circular orbit. So you know how you used to learn that all squares are rectangles, but not all rectangles are squares? Well, all circles are ellipses, but not all ellipses are circles. A circle, in the terms of an ellipse, are when the 2 focuses coincide, and we call that at the center. All right? So now, not moving in circular orbit, this observation was a huge blow to the centered, well, of course it's a huge blow because it says everything rotates around elliptically with the sun at a focus. All right? And again, the retrograde motion is described very easily if we're all orbiting around the sun. We just orbit at different rates, and that completely explains the way retrograde motion. So let's look here. Orbits are defined by its semi-major axis A and its eccentricity E. An eccentricity of 0 corresponds to a circle. And you'll notice that the eccentricity of Earth's orbit is not 0, but it's pretty darn close. Okay? The second one is the law of Kepler's laws, is the law of areas. So this is that a line that connects a planet to the sun sweeps out equal areas in the plane of the area's orbit in equal time intervals. That is the rate dA dt that the area changes is constant. So this is found to be the equivalent of the law of conservation of angular momentum. All right? And let's see what that means with this thing. So if we look at a time, so if we look at this, let's make a line and have it sweep this area, and then let's look at it sweep this area. If it takes the same amount of time, right? So say this takes 2 months, and this takes 2 months, then these areas, I'm using the R here, so then this area here, hold on, A2, I'm using their R as well, but so A2 and A1, if it's the same amount of time to sweep them out, then the areas are equal. What I mean by that is that the time it takes to go from this point to this point is equal to the time it takes to go from the point I'm pointing at here to the point I'm pointing at here. If those two time intervals are the same, then A1 and A2 are the same. All right? And again, that can be seen as equivalent to the law of conservation of angular momentum. Now, Kepler's third law is that the square of the period of any planet is proportional to the cube of the semi-major axis. Now, this is where this is unfortunate that we do this. Kepler said that astronomy classes do a better job of this. You can see the law of areas here. But what Kepler really found is that t squared is proportional. That's what that little alpha fish means there, to r cubed, where r cubed is the average distance. Kepler did not figure this part out. This is what Newton brought to the table. All right, and it holds for elliptical orbits. If we replace r with a, r again can be an average distance, or a can be an average distance, or however they define it. Oh, it says it's to the semi-major axis. That's new. Usually they say average distance, but yeah, if you do that semi-major axis, that's fine. And if you look here, this is the semi-major axis. You'll notice it's major because it's bigger than that one, which is the semi-minor axis. So what this allows us to do is, you'll notice if you launch something like, say, a satellite that you measure very carefully and that you know exactly how much mass it has, if you know its distance that it's orbiting the Earth from, and you measure with a watch its period, you can measure the mass of the Earth fairly readily. All right. Now, you won't get it super precise, but you can get its order of magnitude, which is really something. And then once you have that mass of the Earth, you can do the same thing with the Earth rotating around the sun, and you can get the mass of the sun. So you can use Kepler's third law, since you can't put planets and stars on a scale, obviously, but we have masses for all of them. We can look at things orbiting near them, and the same thing with black holes and galaxies and all sorts of things. We can figure out their mass using this law. Okay? And again, Kepler's laws were folded into Newton's theory of gravitational motion. All right? So we can see here Kepler's laws of periods for the solar system. You'll notice this is the data. No, the solar system does not end at Pluto. So Pluto is called the Kuiper Belt object. And so the solar system, sort of, it's in regions, right? You have the sun, you have the inner solar system, which ends at the asteroid belt. You have the planetary system, which ends at the Kuiper Belt. And then these are all pretty much flat, all right? Then you have a spherical Oort cloud of comets that extends out very, very far. Basically, if you look at the solar system dynamics, can be a little more complicated based on the flow of the sun's plasma. So it can actually be very long. That the effect of that plasma can be very short at some parts of the solar system and very long at others. If you look at the path of Voyager. And so one of the things we're looking at with the Voyager satellites is where to define the end of the solar system, right? And so, so I believe the point they have, one of the definitions they have now is when particles interacting with you are dominated by interstellar particles rather than the sun's particles, right? When the sun is just lost in the noise, they're calling that the end of the solar system. And there's like this shock wave that happens when you cross from one to the other, which they thought would be severe, but was not as severe as I thought it would be. The Voyager satellite seemed to do okay with it. So I don't want to do the reason that this checkpoint isn't there is, again, we're not really focusing on examples. We're just talking about this. Everything in astronomy is pretty big. So if you guys want to have your minds blown, I will give you a link for you to watch after class, and we can discuss it tomorrow. For a little bit, not the whole time. But this is one of my favorite videos I showed to the astronomy students. Hold on. If you wanna get a scale of the universe, let me go to the YouTube. Where's the one I like? There's a lot of these, but here we go. This is the one I like. All right. Hold on. It's going to a timestamp. I just want to be sure. Yeah, I'm doing that right now. I do teach astronomy. So if you click on that link, let me make sure it works. Yep, it works. Good. I had to make a small adjustment for the timestamp, but oh, it's going forward on my computer. You can hear it. So yeah, that'll give you, if you want to see how big the video is, that is the that will give you some idea. But yes, I do teach astronomy. Astronomy is a lot of fun because, you know, it's a terminal science class, so I don't worry about their math too much. Unlike you guys, you have to do a lot more science, so I got to worry about your math and your details. Okay. So going forward, we have orbital energies of satellites, and that's about it for the chapter. So we'll call that a chapter. So actually, I'm going to say I've taken the attendance. So actually, since we have 10 minutes, I'd say watch the video I just put on if you want to see the size of the universe and see how big it is, and we can talk about that for the last 10 minutes. Otherwise, you're free to go. And I'll stick around. I'm going to figure out, while you're doing that, I'm going to figure out how to send this survey to everybody. Yeah, be on the lookout for that survey. It's coming to today soon. And let's see here. I'm gonna see if I can figure it out on Wiley Plus, then I can send it to all the sections. So I might do that. If not, I'll just do it through Blackboard. Yeah.
Professor, the exam is not on Tuesday. The possible date is gonna be on Thursday, right? If the final exam is not on Tuesday.
I had it down on my calendar as Tuesday, like because this class does its exams on Tuesdays, right?
Right.
So that's why I have it down on that Tuesday.
Okay, so it's on Tuesday, definitely on Tuesday.
Yeah. Well, okay. Again, like I said, unless there's huge protests about it, but so far no one has protested, so you would be the only one at this point.
Okay, I see. Yeah, it's fine. I just want to know so that because we have other. Yeah, I can plan on it. Yeah.
Yeah. Thank you. I hear you. I hear you. No problem. Let me see. Select students. All right, it looks like Wiley Plus is making this hard, so I'll just send it over Blackboard. Probably should have done anyway. Oh, I gotta stop recording, otherwise the whole